Okay, let's get started. Welcome, everyone. My name is Stefan Güttel. I'm a lecturer in the Department of Mathematics. My research interests are in numerical linear algebra and numerical analysis in general. So I'm using Matlab a lot for my work, and I'm very excited to tell you about Matlab. Some of you might already know Matlab. You might still find this course useful, maybe as a refresher. Okay. First things first, these sessions are recorded. So if for some reason you're not happy to be on the video, then turn off your camera. I see nobody has currently their camera on anyway. I believe you should not be able, you will not be visible anyway in the recording because I have spotlighted my own video, right? Of course, it's appreciated if you turn on your camera and if you ask questions via your microphone. I think it makes for a more interactive session, but it's completely up to you. Secondly, there are notes for this course which are available on a website whose link I have just posted on the chat. So please have a look in the chat and see if you can locate this website that you also see on my shared screen. Just noting that there is a typo here. It should be Matlab, of course. And if you scroll down on this website, you will find a link to the course material. So that's the PDF we will be following quite closely. If you have any problems locating this website, please let me know in the chat. Furthermore, I believe you have already been informed that Matlab is freely available for you and that you should download it before the session. I'd just like to understand if this has actually happened. So I'm going to launch a poll now, which you should see on your computer. Hopefully this pops up now. Can you please indicate whether or not you have managed to download Matlab? Okay, so I've got the results. About 60% have managed to install it, and about 23%, so 5 of you have not tried yet. And there are 4 that might have had problems installing Matlab. Now, I can't fix them now during the session, but what I would suggest is if you have some fundamental problems getting Matlab running on your computer, please let me know by email, and I will try to have a look into this in the break. We will have a break between 12 and 1 o'clock PM time. So I'll have a look at that. You should still follow the session because I will just demonstrate everything on the screen. So it might still be useful even though you can't really try it out on your computer as of yet. You can also use Matlab online if you like. That's perfectly fine. Right, I'm going to share this. Great. So if everyone has located the PDF file, I'm going to bring it up here as well. This is a crash course, so I will be rather quick, but hopefully it will be useful for you later on to go back and basically use this as a reference. There are 10 topics that I would like to cover, starting with an introduction. We will talk about matrices and arrays, learn about Matlab expressions, and then most importantly, what Matlab is really good at is linear algebra computations. So we will look into these. You can use Matlab quite easily to generate nice graphics for your project that you might be writing at the end of your degree program. You see some example plots that I have included in this document here. So these are all generated with Matlab. We will learn about programming and functions, and then I have just picked one topic that is a bit more advanced out of many topics that I've chosen. So this is just as an example. I will go a bit deeper into numerical integration and differential equations with Matlab, and then conclude with some useful tools and tricks. And also there is a very simple assignment which counts 5% towards your transferable skills unit. So it's a rather small fraction. Hopefully you will find this assignment useful for materializing what you have learned with me in this course. I have the chat window open on my second screen here. By the way, if you see me looking left and right, that's just because I have several monitors here, right? I have the chat window open, so any immediate questions that have to do with the content of the course, feel free to ask them on the chat. But you can also use your microphone and interrupt me, just as if we were sitting in the same room, which unfortunately we are not at the moment. But feel free to use your microphone and ask questions. You should also be able, so if you have Matlab started on your computer, you should also be able to share your screen with Zoom. So at the bottom of the Zoom app, you see all these buttons there. If you like, you can share your screen because it would allow me to have a look at what you're doing in Matlab as we type along, and I can give you some more direct feedback there. So feel free to share your screen if you like to. Okay, so let's get started with the introduction. This is a 4-hour course. As I mentioned, it will be rather quick. The good thing with Matlab is that there is an excellent documentation built into Matlab itself. So actually what I have done in creating these notes is I have mainly followed Matlab's own documentation. So what I'm going through here is basically a crash course or a short summary of Matlab's demonstration. Matlab's documentation. There are 2 commands that are most important to know of in Matlab, and you see I have my Matlab open here. Just to give you a brief overview of what we have, you should see something very similar. On the top here, you have the menu bar, which might look slightly different because you might be in another tab, right? But the home tab is the most important one. This is where you can create scripts. You can change your preferences. You can set paths. I'm not going to be using this much here. And yeah, this is really the main tab that we will be using most of the time, right? So creating new scripts, opening them and saving them. So that's the top. Then here on the left, we have the view of our current folder. So here you see in my screen an address bar. So this indicates the current working folder I'm in. You see that I'm within Dropbox, then something else, 2020 teaching, and the content of the folder is listed here. Now at the moment there is no content because this folder is empty for me. I have not created any Matlab files, but if I were to go on new script and I would then save it, Matlab would ask me about a name, and I'm just going to demonstrate this quickly. I call this my script, like that. And it would appear on the left here. So all the files, all the Matlab files that we create will appear here. Then this is the command window in Matlab. This is where you can type interactively Matlab commands. So you can just type commands here and Matlab will interpret them immediately. So when you hit enter, it will be executed. And on the right, you have the so-called workspace, which collects all the variables that we currently have in memory. So just to give you a quick overview, I can create variables like so. I just type x is assigned the value 2. So that's the notation here, x, then there's equals symbol 2. But note that I have not said x equals 2. And the way you should really read this is from right to left. The number 2 is assigned to a variable called x, right? This is how we will be reading this throughout the course because it's actually not checking for equality or something like that. It's different. It's an assignment of a variable. So when I type this and I hit enter, then you will see in the workspace on the right, I now have a variable by the name x and its value is 2, right? And all the variables that we have in memory, I can now, for example, compute x plus 3 if I want to, and it will give me an answer which is 5. All the variables that are in memory are shown in the workspace here. The last output that I have produced on the command window is also available as a variable called ans, so for answer. So whenever you want to use the result of your last computation, you can also type ans. So for example, if I want to square this, that would give me 25. And now, of course, the value of ans has changed to 25 because this is always the last output that we have produced in the command window. Okay, so these are the most important components, the menu bar here, the current folder, the command window in the middle, and the workspace on the right. Now, I mentioned already, Matlab comes with a very, very nice documentation, and you can access this by typing doc in the command window. So if you just type doc and you hit enter, then it will open up Matlab's documentation, which looks like that. Matlab comes with some core commands that are under the category Matlab in this documentation. So you see on the left, you have the content, and one of the categories is called Matlab. And this is what I have followed in order to produce the notes that we are following, basically the getting started with Matlab section. But then Matlab also has many packages. You might have some of them installed on your computer, and the documentation for each of these packages is also listed here. So there's, for example, a bioinformatics toolbox, there's a deep learning toolbox, signal processing toolbox, and so on. This will slightly differ on your installation because you might have more or you might have fewer of these toolboxes than I have installed here. So that's the documentation. And if I want to find out about, for example, computing sums in Matlab, I can just type, for example, sum here up in the help. And then I will get a list of all the functions that are available for computing sums. So when I click on this entry here, it will give me an explanation of the syntax of the sum function. It will give me a description of that function. And then what is usually very useful is that we also get a lot of examples. So there is Matlab code that we can just copy and paste to our console and execute, right? So that's very useful for learning about functions in general. So this is the documentation. You can type doc sum if you already know that you want to find out something about the sum function, and it will immediately go to the page that we have just found. If you don't want this extra window to open and you're happy with just reading the documentation in the command window, you can type help sum as well. So when you type help sum, you get a condensed version of this documentation page, just outputted directly to the command window. This is usually what I would use when working with Matlab, and I quickly need to look up the syntax of a function. I would not go to the documentation, but I would just type help and then the name of the function I'm interested in. It's usually good enough, right? Sometimes the formatting is a bit messy, so if you want to read these tables nicely, then having a look at the documentation might be worth it. But in general, I find this good enough already. And there are examples as well, okay, to try out immediately. So for example, I can just copy this here. In fact, just select it with the mouse. And when I hit enter, the selection will automatically be executed on the command window as an example here. Right, so these are really important functions, help and doc. They are also listed in this document here, which I'm following in the first paragraph. So make sure you remember them. Apart from the documentation that is shipped with Matlab, there are some very good tutorials and books available. In particular, on the MathWorks website, there is a user community, which is called Matlab Central. So there you will be able to post questions to other Matlab users, and they are usually very helpful to answering them. And also you will find a collection of Matlab files posted by other people. So if you are struggling with a particular problem, maybe it's worth having a look at Matlab Central and finding out if someone else has already pretty much solved the same problem in Matlab before and they have posted their code. So that's a very good resource for getting Matlab files. Then there are two books written by Cleve Moeller. Cleve Moeller is one of Matlab's authors, one of the inventors of Matlab. And his books are available on this website here, ukmathworks.com/Moeller HTML. Let me just see if I can bring this up here. There we are. Just clicking this away. So there are two books. One is called Numerical Computing with Matlab, and the other one is called Experiments with Matlab. Both of these are freely available for download. So you can just have a look at them. And they have some very interesting problems that are solved with Matlab. It's very versatile. You can do many things. For example, there is a Matlab code that scrapes the internet and downloads web pages and computes the page rank for a selection of web pages. So similarly to what had been used by Google in the early days in order to rank web pages. Okay, you find examples like that in the Experiments with Matlab book, which I find very nice. So I recommend having a look into these. They are freely available. We also have a very comprehensive Matlab guide written by Des and Nick Hyam. Nick Hyam is one of our own Manchester-based professor in our department. And that is really the go-to guide in order for learning everything that there is to know about Matlab. Right? It's quite a big book. It's available in our library as well. So these are really the main references that you would need. I don't think you would need any other books in order to get started with Matlab. Okay, let's have a look at Matlab itself. I already mentioned the command window, workspace, and the command history, and the navigation in the Matlab's documentation. We will talk about comments a little bit later, so I'm going to skip this for now. But one thing I would like to point out is if you are with the cursor in your command window, then you can retrieve the last Matlab command that you have entered by using the arrow key on your keyboard. Right? So this is my keyboard here. I don't know if you can see that, but if you go arrow up once, twice, 3 times, and so on, you will cycle through the previous commands that you have entered. So this is usually very useful because you don't want to type over and over again the same stuff. So you can go back and forth with these with your mouse keys, with these cursor keys on your keyboard. Okay. That's very useful. What else? We can also use the tab key for auto-completion. So if you have a, let's say, variable with a very long name, so here's a variable called a very long named variable, which has the value 7, and you want to use this in a computation, it will be quite tedious to actually type this over and over again. So what you can do is you can just type the first few characters and then hit the tab key on your keyboard. The tab key will automatically complete this variable name for you. And if there are multiple ways to complete it, because maybe you have also a very long named variable 2 in your computer's memory, then the tab key will give you a suggestion for the 2 possible completions that are currently sensible. Right? So cursor up and tab key are very useful in Matlab in order to speed up coding. All right, then there is a command called exit, which please do not type at the moment because it will just close Matlab. So you can close Matlab by just typing exit, or you can close it up here. On Windows and on Mac, it would also be a similar way of closing it, just as you close any other program. That's exit. And then a very important key combination is Control and C. So I'm going to just type this here. So if you locate on your keyboard the Control key and the C key, if you use both of these in combination in Matlab, it will interrupt the execution of your computer code. I believe on a Mac, it would be Command plus C, right? So these 2 keys together are quite useful. When do we need this? Well, we need it when we have a very slow Matlab program and we are just not patient enough to wait for it to complete, or if we are maybe stuck in an infinite loop. So let me just demonstrate this. I will create an infinite loop in Matlab by typing in the command window while space 1, comma, end. What this does is it creates a while loop that keeps on looping forever because the while condition, the running condition is true for all times. So this loop will never stop. So when I hit enter, then you see that we are not going back to the prompt. I'm not able to type in anything here. And at the bottom left of my Matlab window, it tells me that Matlab is busy. So this is how we tell that it's currently doing something and we are waiting for it to finish. But of course, this will never finish. So now I need to use Control C. And this will stop the while loop. Okay, there's a question on the chat. If you're installing Matlab currently, if you get a list of products and toolboxes that are available for you, I would recommend to select all of them. Otherwise, for this tutorial and for most of your studies, you will be fine just without any toolboxes, actually. We'll just use plain Matlab. Right? So please don't buy any additional toolboxes. Just use whatever is available in your current Matlab download. But select all of them. Okay, so very important, Control C. Now, you will see that in my short summary, at the end of each or at the beginning of each of these sections, I have a list of useful commands, right? So what I'll do is I will just very briefly talk you through all of them. You might make notes as we go along, but really this is the main reference. So for example, I will now tell you about the CLC command. But maybe tomorrow or the day after you have forgotten what I explained about that and you just want to recap what CLC actually does, then you can always type help CLC. Okay. And it will give you a detailed or more or less detailed description of what this command is used for. And that's why I think it's good enough to actually have a list of these useful commands, because you can get detailed information about any of them by just typing doc and then the name of this command. So now that we are at it, CLC, one of my favorite commands, it just clears the command window. So we are back to a very clean setup. It doesn't delete any of the variables. So the variables that we have previously created, they're still in memory, right? So my variable X is still here and my very long named variable with value 7 is also available. If you want to delete a variable which you have in memory, you can type clear space and then the name of that variable. So clear X would remove the variable small x. And you see Matlab is case sensitive. So there's still a variable called capital X in memory. So if I want to clear this one as well, I need to type clear capital X. If you want to start fresh and you want to get rid of all of the variables you have in memory, then you just type clear all. Okay, and now we are back to square one. We have an empty command window. We have an empty workspace. That's just as if we had just started up Matlab. Right? It's always a good idea when you start like a new project or a new script, or you want to try out some things. It's a good idea to clear the workspace first, because you might have some variables still in memory that will give you unexpected results in your computations. So it's a good idea to clear repeatedly whenever you don't need the old variable data anymore. And that's actually all the commands I wanted to cover in this introduction here. We can now ask, are there any questions regarding the introductory material, or do you want me to move on to the next section? If you have any questions, please type them in the chat. Okay, there are no questions, so I'm going to continue. So Matlab stands for Matrix Laboratory. So it's really an environment for working with matrices. Right? Everything revolves around this data type of a matrix. And yeah, so the most important data structure is a matrix. So what we will learn now is how to create matrices, how to concatenate columns, and so on. There is a list of commands listed here. It's a rather long list, and I will go through them quickly now, one by one. Okay. So first of all, in Matlab, we can create empty matrices. Matrices are just arrays of numbers, right? So you have, let's say, 5 rows and 3 columns. You can think of a matrix as a table with a number of rows and a number of columns. You could have a table or a matrix that has no entries at all. That is the so-called empty matrix. And matrices are just defined with square brackets. Okay, we do everything with square brackets here. So this defines an empty matrix, and I could give it a name as well. I could say this is my matrix A, which has 0 rows and 0 columns. It's a rather boring matrix. Most often we deal with matrices that have entries, and a special case of such a matrix would be a vector. Right? A vector is just a matrix that has either a single row or a single column. So this is the definition of a vector X, which has 3 entries, and they are arranged in a single row. Right? So whenever we use commas to separate entries, we are talking about going from left to right. Okay, so this would be an arrangement of 3 numbers in a row, a so-called row vector. By the way, you can create comments in Matlab by using this percentage sign. Everything that you type after the percentage sign is ignored by Matlab. So it can be used to add some human readable explanation to what we are doing at the end of each Matlab command, let's say. So just for us to remember, this defines a row vector. And when you hit enter, you actually see that, yes, 1, 2, 3 is here printed out on a single line. So that really seems to be a row vector. How do I get a column vector? Column vector is obtained by replacing the commas with a semicolon. Okay. So I'm going to type 1 semicolon 2 semicolon 3. And I now hit enter. This produces the more familiar format of a vector, which is a column vector. And now we can combine rows and column operations in Matlab very easily by mixing in a compatible way commas and semicolons. So let's say I want to create a matrix which has 2 rows and 3 columns. In the first row, I want to have entries 1, 2, 3. And in the second row, I want to have entries, let's say 7, 8, 9. Okay. Then I can do this as follows. I type 1, 2, 3 within the square brackets, then a semicolon to get to the second row, and then 7, 8, 9. So when I hit enter now, I will see that A is a matrix which has 2 rows and 3 columns. That's nice. So we have created our first matrix, which is not just a vector. And now we would like to access an element of that matrix. So how can I, for example, get this entry 8 in my matrix? Well, I need to tell Matlab that I want the element in row 2, which is the second row, column 2. Right? It's always row first and then column. So row 2, column 2, that's the element 2, 3 in our matrix. And now we're using round brackets here. Okay, so in order to retrieve elements from a matrix, we use round brackets. And indeed, this element is 8. If I want to access the element here, I would have to go to the second row, third column. So A2, 3, that should give me the element 9. Okay. So important to remember, it's always row first, column second. Let's create another matrix. I will call it, let's say, B. And I want this matrix to have, let's say, 3 rows and just 1 column. So that would be actually a vector. And my entries will be 2, 4, 6. Just picking some random numbers here. Okay, so that's my matrix B, which happens to be a vector. Then I can multiply A and B. So matrix multiplication is something that hopefully you are already familiar with. But I just want to, because it's so fundamental to our course, I just want to give a very brief refresher of matrix multiplication. Okay, so let's say we have 2 matrices, one of them called A, which has entries A11, A21 up to AM1 in the first column. And then we have A12, A22 up to AM2 in the second column. And overall, we have n columns. So the last column will have entries A1n, A2n up to AMN. Okay, this is my matrix A. And you see my indexation is always, first I'm addressing the first index always refers to the rows. So this would be the row index. And this is the column index. And so that's why Matlab uses also the same notation. So this is very standard in numerical linear algebra. First the rows and then the columns. So this is my matrix A. And let's say I have another matrix B. And now importantly, I want this matrix B to have n rows, where n is the same as the number of columns that my matrix A has. So this matrix has entries B11, B21, sorry, up to Bn1. That would be the first column. The second column is B12, B22, up to Bn2. And let's say we have overall maybe P columns. So the last column would be A1P, B2P, up to Bn P. Okay, so how do we define the matrix product A times B? Well, A times B turns out to be a matrix, and it will be a matrix of size as follows. It will have as many rows as our matrix A has rows. So in other words, there will be m rows, and it will have as many columns as our matrix B has columns. So in other words, there will be P columns. Okay, so if you multiply an m by n matrix with an n by p matrix, the product is an m by p matrix. Now let's call this matrix C, let's say, and let's say the entries are defined as Cij, right? So we have lots of entries here, and every entry Cij is denoted by a small Cij. Then we can write down the formula for each of these. So it turns out that Cij is a sum for k ranging from 1 to n of A I k times B k j. Okay. So this is really how matrix products are defined. Now, if you look at this carefully, what do we have here? If k ranges from 1 to n, that means we are traversing here a row of A, right? Because we are increasing k here, so we are going from left to right over a single row of A. And also here, k is actually the k now ranges over the different rows over here, so we are actually going along a single column as k increases from 1 to n. So in other words, this multiplication is defined by selecting a row of the matrix A and a column of the matrix B and computing an inner product, because this is like the inner product of two vectors. So for example, if you want to know what is the entry in the 2, 2 position of this matrix product A times B, so that would be C22, you need to take the second row in that matrix and compute the inner product with the second column of the second matrix. Okay. So this gives you the entry C22. If, for example, you want to have the entry C2P, which would be this one here, what do you have to do? You also have to take the second row of matrix A and the pth column of B. So like this, we get all the entries of the matrix C. It's really just computing inner products between the rows of A and the columns of B. Okay, that's one interpretation of matrix multiplication. The other one is that you actually take linear combinations of the columns of A. But for now, for the moment, I will just stick with this definition here to keep things simple. All right, so just remember that in order for two matrices to that we can multiply them, they need to have consistent dimensions. So A needs to have as many columns as B has rows. And the product is defined by this formula here. Okay, so that's what's going on when we compute in Matlab A times B, right? So this is actually a matrix. It's a matrix vector product. And remember, our matrix A, I just bring it up here, has only 2 rows. Therefore, the matrix vector product A times B is a vector with 2 elements. Okay, so that's how we compute matrix vector products, just with the multiplication symbol. Let's say you have some matrix X with entries 1, 2, 3, and maybe another matrix Y with entries 7, 8, 9, for example. I can also multiply them component-wise, right? I want to multiply the first entry in X with the first entry in Y, the second entry in X with the second entry in Y, and so on. How do I do that? Well, typing X times Y will not work because X times Y is matrix-matrix multiplication, and these two matrices X and Y are not consistent. I cannot multiply two row vectors in this fashion because they cannot be multiplied. So this will lead to an error. Okay, incorrect dimensions for matrix multiplication. So if you want pointwise multiplication, you have to put a full stop in front of this multiplication symbol. So X dot star refers to pointwise multiplication. And here you indeed get 7 times 1, 2 times 8, and 3 times 18 in the answer. You can also do pointwise division. So if you type dot /, you will take the entries of X and element by element divide them by the corresponding element in the matrix Y, and here you get the corresponding quotients. All right, some other commands that are listed on the handout. Of course, you can add vectors easily. So X plus Y will just give you the component Y's addition. You can subtract them. There is a function called sum. So if you give sum a matrix, let's say A, let's just remind ourselves what this matrix A was. It's a 2 by 3 matrix. So if I compute sum A, then what it does is it will sum the entries column by column. You see in the answer, we have the sum of the first column, the second column, and the third column. If you want to sum along the rows, you will have to give the corresponding argument. You need to type sum A, 2. So this will now sum from the left to right. So the sum of the entries in the first row is 6, and the sum of the entries in the second row is 24. How do I know that I can call the sum function like this? Well, if I type help sum, then it will tell me that I can give a second dimension to the sum function as an input, a second parameter, and this will then sum along the corresponding dimension, either the first dimension, which is along the columns, or the second dimension, which is along the rows. Likewise, there is also a function called prod, which you can use to compute products along rows and columns. There is a function called transpose, which basically exchanges the rows and columns of a matrix. So just recall, this was our original matrix A, and this is A transpose, right? So you swap the columns and the column and row indices. So out of a 2 by 3 matrix, you create a 3 by 2 matrix using the transpose command. There is a function called diag, which just returns the diagonal entries of a matrix. So this matrix here, it's not a square matrix, but we can still define the diagonal entries as the one where the column and row indices are the same. So this is entry A11, this is entry A22. So these are the two diagonal elements of A, and that's what we get by calling diag. If you have a vector in your computer's memory, let's say X, and you type diag X, then Matlab will create a matrix which is 0 everywhere except on the diagonal, and the diagonal entries are exactly the ones in the vector X. So this is how you can create a diagonal matrix. Very important in Matlab is the so-called colon operator. So if you have, let's go back to this matrix A that we already have in memory. If you want to address all the elements along a certain dimension, then you can use the colon operator for that. So for example, if I want to get only the first row of this matrix, then what I can do is I can say A1, right? That addresses the first row, comma, and now I type here not an index of the column, but I type a colon. So this colon just means take everything that is available in this range, and it would give you all the elements whose second index is between 1 and 3. So it will give you exactly the first row of the matrix A. That's a very useful operator. If you just want all the indices starting from 2 going up to 3, let's say, you can just type 2:3. So the start index comes before the colon, and the end index follows the colon. Let me first create a slightly bigger matrix using another command called rund. So if I type A is assigned rund, and let's say 7,9. This will create a 7×9 matrix having random numbers for its entries. These numbers are uniformly distributed between 0 and 1. So this is a slightly bigger matrix. Now we can also try out the following. If I want, let's say, all the rows of my matrix with indices 3 up to 5, and all the columns of my matrix with indices, let's say 4 up to 7, I can use this notation here. So this will select a submatrix of A according to these dimensions here. Okay, so this will be a submatrix of A, and we have selected the corresponding rows and columns by these indices here. Let's say another use case. Let's say you want every other column of the matrix A. Right? So this is my original matrix A, and I want to only keep the first, the second, the fifth, and so on column of A. How do I do that? Well, I want the full column, so the first index should be a colon, right? I'm not specifying the row. And now I want the first column, and then I want to go up to the end. And this is the end keyword here, in steps of 2. So if you have 2 colons, then you have to read this as start index, increment, and final index. Right? So this will extract columns 1, 3, 5, 7, and 9, because our matrix has 9 columns. And there we go. This is the corresponding submatrix. Okay, so this colon is a very useful operator because you can use it to quickly extract elements of a matrix. There's also a command called rundn. So this gives you normally distributed random numbers. So they can also be negative. They follow Gauss distribution. You see here I get a few random entries. And of course, you can use it to create matrices with random numbers in them. So here's a 3×3 matrix with random normally distributed numbers. An important command as well is Linspace. So Linspace allows you to create a vector whose entries are equally spaced or equidistant to each other. So let's say we want to create a number of, let's say, 50 points starting at 0 and going up to 9. Then I can type Linspace 7, 9, 50, separated by commas like so. And I can assign this to a vector x. So this returns a vector with 50 elements, and you see the first one is number 7, the final one is 9, and all the others are equally spaced between them. Right? So nicely equispaced entries. So the Linspace command is useful in quite a number of cases. The zeros command creates a 0 matrix. So if you want a matrix with entries all 0, then you can use zeros. For example, here I have created a zeros matrix with 5 rows and 4 columns. If you want a matrix with which has only entries equal to 1, the command is ones. I is the identity matrix. So if you want the identity matrix of size 4, you can just type I4. And you see that's the matrix that has zeros everywhere except ones on the diagonal. And then there is a useful command called gallery. So we type help gallery on the command line. We will see a long list of names of different matrices. So these are special matrices that appear often in applications or in the scientific literature. And we can call them by their name and quickly generate these matrices. So for example, there's a matrix called Forsyth matrix, and the corresponding name in Matlab's gallery is Forsyth. Or there's a matrix called Tridiac. Where is it? Tridiac. which is a tridiagonal matrix that we will see in a short while. So just to show you an example how to create one of these matrices, you just type gallery, again brackets because we are calling a function name, and then here we are specifying the name of the matrix we want, and then usually there is another parameter or maybe two parameters that need to be specified. So let's say I want to create a tridiagonal matrix with, let's say, of size 5 by 5. I have to type tridiag 5, and I will call this matrix A again. Okay, so this is how I use the gallery. Let's type enter. Now we get a kind of unusual output. Okay, so what is this? What I'm seeing here are the entries of the matrix A, and it looks different than what we have seen before. Right? This is the so-called sparse matrix format in Matlab. And you can see this in the workspace. The matrix A is defined in our computer's memory, but its value is 5 by 5 sparse double. So what is a sparse matrix? A sparse matrix is a matrix most of which entries are 0, and it is therefore pointless to store these zeros explicitly. Right? Let's say you have a matrix that is of size 1 million by 1 million, but there are only like a handful of entries that are non-zero. It would be kind of silly to store all these zeros in our computer memory. So in the sparse matrix format, what we do is we list the position of all the entries. So for example, there's an entry in position 2, 1, which is the second row, first column, and the corresponding value is -1. Right? So these are all the non-zero elements of the matrix. And you see there are some missing indices. We have a 5 by 5 matrix, so really we should see 25 numbers here, but we only see a handful. Most of the all of the others that we don't see, they are actually 0. If we want to see this matrix in its full glory, we have to type full A. So full takes a matrix and converts it from sparse to a dense matrix format. So if I hit enter here, I will indeed see that A is a 5 by 5 matrix, but now it's printed in dense format. You can also take a dense matrix and convert it to a sparse. So if I say that B is full A, I can convert back to a sparse format by using the command sparse. And I'm back to my sparse matrix format. If you have a huge sparse matrix in memory, it's not recommended to type full and then convert it back to a dense matrix format because you might run out of memory. Right? So usually if a matrix is stored in sparse format, there's a good reason for that. There is a function called size. So if I type size A, I get a 2 vector as an answer, so 2 elements, and they correspond to the number of rows and columns in my matrix. So if I type, for example, size X, I'll get that this matrix X has 1 row and 50 columns. Right? It's a row vector with 50 elements. For vectors, you can also just type length. It will give you the larger of the two outputs as the length of the vector. Okay, any questions on these commands? I don't see any. So what I would like to do now is, hopefully you have Matlab open and you have tried to follow along. I would like to give you a few minutes time to go through some of the exercises. So in the handout, there are 3 exercises, all relating to this second chapter, exercise 1, 2, and 3. And we'll just have a, let's say, 5 minutes break where you can attempt solving these. Okay, so the first one is about creating a matrix A that looks like this, using only a single line of MATLAB code, and then do some subsequent operations on it. So we have already learned how to create matrices. Just as a tip, it might be a good idea to try to create this initial matrix A by a product of 2 vectors. Right? Can you generate 2 vectors, let's say X and Y, so that the product of these 2 vectors results in the matrix A? Okay, that would then be a single line of MATLAB code. Then we want to assign random numbers to the second row of this matrix. How do we do that? And then we want to assign the first row of this matrix so that all columns sum to 0. Then reorder the columns reversely and transpose the matrix. So just for you to try out some things. And if you are done with that, then you can attempt exercise 2 and 3 as well. Okay, so 5 minutes time. In the meantime, if you struggle or if you want to show me what you're doing on the screen, feel free to share your screen or type any questions on the chat. Okay, I suggest that we continue. I'm gonna quickly do exercise number 1 together. So in order to create this matrix, we can realize that it is a matrix of rank 1. There's only one column which is linearly independent of the others. I mean, we have 2 rows. We have 2 0 rows and 1 non-zero row. So a so-called rank 1 matrix can be created as an outer product of 2 vectors. Now, what are the 2 vectors that I need here? Well, I have only entries in the last row of this 3 by 5 matrix. So what I'll need is a row vector that has zeros in the first 2 positions and a 1 in the final position. Okay, that's my first vector. And my second vector is just the multiples of this vector that I need for each of the columns. So the entries are 5, 4, 3, 2, 1. So one way of doing it is to say 5 colon minus 1, 1. So remember, the colon operator creates basically all indices or all numbers starting with the starting index, going down to the end index in steps indicated in the middle. So this here would create the entries 5, 4, 3, 2, 1. Put them in a would put them into a single row vector. Now, if I multiply a column vector by a row vector, I will get a matrix. Okay, so let's see. That seems to be working. So this is the matrix A generated by a single line of Matlab code. Now we want to assign random numbers to its second row. How do I do that? Well, the second row is obtained by typing A brackets 2, colon, right? This addresses the entries in the second row. And I want to change these to random numbers. So let me just use rand. Now, what size of matrix do I need to put there? Well, I need a row vector, so I need 1 row and 5 columns. So rand 1, 5 will do the trick. There we are. We have just changed the second row. And now we want to assign the first row such that all columns sum to 0. Now remember, by typing sum A, I will get the sum of the entries of A along the columns. So all I need to do is I need to put the negative of this into the first row of our matrix. So A1, colon should be minus sum of A. Right? So we'll get this, and we can now double check that the columns sum to 0 as they should by just typing sum A. Now you see an interesting effect here because we are working with floating point numbers. We do not expect to get exact zeros when we do this operation. Indeed, the last entry is 10 to the minus 15, 10 to the minus 16 actually rather. But that's perfectly acceptable because we are working in double precision here, right? So we do not expect to get exact zeros due to some floating point errors that we are making. We are not done yet. The next job was to reorder the columns reversely and transpose the matrix. So how do we do that? Okay, if I want to get the columns of A in reverse order, I need to address them. So I want to take all the rows and I want to start with the last column of A, going down in steps of -1 until I arrive at the first column. Okay, so A colon, end colon -1 colon 1 would do exactly that. So this should produce the reversed version of A, the column reversed version. And you see that this was the first column, has now been teleported into the last one. And then we have here the second column is the second but last, and so on. So this worked. And finally, we want to transpose that matrix as well. So I can just type transpose here. Okay, that's basically the output that we wanted for this exercise. Just as a small tip, transpose is quite an important command. So if you don't want to type transpose, you can also type dot quote, like this single quote character. Okay. This does the same thing as transpose. It's exactly the same iteration. You might wonder, why do we need this dot here? Because this is, again, an element-wise operation. If you just type the quote symbol like this, you get the complex transpose of a matrix. Okay, so a complex transpose is obtained by transposing the matrix, but also taking the complex conjugate of each entry. This matrix has only real entries, so really doesn't make any difference. But if you're working with matrices having complex entries, there is a distinction between dot, quote, and just the quote operator itself, right? So that's just important to keep in mind. I will skip exercise number 2 because this is a very similar problem, creating this matrix in a single line of MATLAB code. Let me just quickly talk about exercise number 3. Here we will create a sparse matrix of size 4. So I want to make this independent of the dimension. So I will introduce a variable n with the value 4. And as you can see, I'm putting a little semicolon at the end of that. You might have seen so far, whenever I type something in MATLAB and I pressed enter, I get the same result back, right? So it basically tells me, okay, I can confirm I've just created this entry or this variable n in my computer's memory, and its value is 4. Most of the time, we don't want that. And you can suppress the outputs by just ending a line with a semicolon. So now you see I'm not getting anything back from the command window. I've just done the same operations, but quietly without any outputs. And I would like to create a sparse matrix that only contains zeros. And the way to do this in MATLAB is using the sparse command. So if you type sparse n, n, then in this case, we are creating a sparse matrix C, all of whose entries are 0. Now, one thing that is of interest as well is, can we actually access the elements of C with a single index? So for example, when I type C12, right, we have already learned this addresses the element in row 1, column 2. But what if I type C, let's say 6? What does this correspond to? Well, it turns out that if you type C6, it will enumerate all the elements of your matrix column-wise. So C6 would correspond to the element in the second column, second position, because we have a 4x4 matrix, right? In the first column, you have entries 1, 2, 3, 4. In the second column, you have entries 5, 6, and so on. So C6 is actually the element at position 2, 2. And we can use this to generate a matrix that is given to us in the exercise. So you see it's this tridiagonal matrix, which has on the diagonal has entries 2. So how do I create a matrix like that? Well, I want to change the entry at position 1 to the number 2. And then I want to skip the next 1, 2, 3, 4, 5 entries to arrive in the next column. So if I now go from 1 to 6, I need to add 5 units. So I'm going in steps of 5, and I want to go until the end of that matrix. So I type C1 colon 5 colon end, and I want all of these entries to be equal to 2. Okay, I'm doing this here. Now, in order to see that we have done the right thing, I will output the matrix in its dense format. So I will just type full C. And you see what we have done. We have changed all the diagonal elements of our matrix C to be 1. Now I want the off-diagonal elements just below the diagonal. I want them to be -1. And the way I do this is I'll take I'll start now from the second element of C, which is this one here. And I will go in steps of 5 and I will assign it the value -1. Let's output the result. Okay, I've changed the subdiagonal. And now I also want to change the superdiagonal. This entry here for a 5 by 5 matrix, if I count column-wise, would be the entry in position 5. So if I type C5 colon, and then I continue increasing in steps of 5, I will end up in the right positions. I want these to be also equal to -1. And now we can look at the result. Here is the matrix that we have created, which coincides with the matrix that we have in exercise 3. Now this matrix happens to be the same as the one returned by the try-diag command in the Matlab gallery. So if I type try-diag 4 and I view the output in dense format, it's exactly the same matrix. This matrix is important because it corresponds to the finite difference discretization, or at least a multiple of the finite difference discretization of the second derivative operator on an interval. We will see this later on in some examples. So this matrix is important. Please keep it in mind. We have on the diagonal a number, in this case 2, and on the off diagonals we have the negative of this halved. Okay, so whenever you see this matrix, you should think about second derivative discretization. Okay, that's the end of section 2. Any questions, please let me know on the chat. I'm now moving on to section 3, which is short, it's quicker. This is about expressions. So there are some special numbers in Matlab which are predefined. Now, numbers are nothing but 1-by-1 matrices. Everything in Matlab is a matrix. So if you define a number, you're really just defining a 1-by-1 matrix. One special number is I. That's the imaginary unit. I believe you can also use J. Yeah, J would also work instead. So I and J are predefined in Matlab as imaginary units. And unfortunately, I and J are also popular indices within for loops, for example. So if you have a counter, we very often use the variable name I or J. So this can actually lead to some confusions. So if you expect I to have the value of the imaginary unit, but actually you have used it in some loop previously, it will be some other value, which might give you unexpected results. Therefore, what I recommend, whenever you want to use the imaginary unit in MATLAB, type 1i. Okay, that just means imaginary part of 1. Even if you have now redefined the variable I to be some other number, okay, like this, 1i will always be the imaginary unit. You can define arbitrary complex numbers by just typing the real part plus the imaginary part, I. Okay, so this would be -7 plus 4i. That's a complex number. That's how we work with complex numbers. There is, of course, a definition of pi. We only see 5 decimal places, but actually there are 16 digits that MATLAB works internally with. If you want to see all of the digits, you can type format long. And if I now again type pi, I will see all of the digits that are available. Right? So format long, it just gives you longer outputs on the command line. And by default, it would be format short e, I believe. So now we are back to the original, or just actually format short is the original format used by MATLAB by default. So that's pi. There is the unit roundoff, which is an important quantity when working with floating point numbers, is called EPS. We have inf, which is infinity, and none, which are not a number operators. So for example, if you type in MATLAB 0/0, that will give you not a number because it's not defined. Whereas if you type 1/inf, that actually gives 0, whereas 1/0 gives inf. Right? So these are just standard numbers defined in IEEE double precision floating point arithmetic. So I think this is pretty much all I wanted to say about these numbers in the expressions section. There are, of course, also standard functions available. So, for example, the exponential function can be just called by exp. So here is the exponential of 9, e to the 9. We have, of course, a log function. So what's the log of 5? Here we are. That would be the natural logarithm, by the way. If you want, for example, the logarithm to base 10, you have to use log 10, or to base 2, the binary log, it would be log 2. And we can compute square roots as well. So what's the square root of 9? That's 3, and so on. So all these standard functions are defined, and they have quite intuitive names, right? They usually have the name you would expect them to have. So we can use Matlab just as a simple calculator. So if you want to compute something quickly, you can just do this on the command line by typing the corresponding expressions and hitting enter. All right, so let's move on to section number 4. Okay. By the way, I'm planning to not make a break here. We'll basically maybe work until like 11:50 or so, and then we'll stop, and then we will resume at 1 o'clock. So let's move on to section number 4, which is about basic linear algebra computations. You see in the handouts that I have emphasized again the difference between matrix multiplication and element-wise multiplication. So matrix multiplication is the star, and element-wise multiplication is dot star. And there is a command called backslash. You can also call it via the function ml divide, which can be used to solve linear systems of equations. So let's try this out quickly. And the way I do this is I will generate a random matrix A, let's say of size 3 by 3. By the way, if I don't give a second index to the random function, it will automatically assume that I want a square matrix. This sometimes causes me trouble, because if I want to create a random vector with, let's say, 1 million elements, that happened to me more than once, I would type something like this, rand n 1e6, so this means 1 million. It's one way to abbreviate 1 million. If I now forget to add comma 1 here, Matlab will attempt to create a dense matrix with 1 million rows and columns, which crashes my Matlab, right? So it's very important to remember that if you only give one index, the second one is automatically assumed to be the same as the first. So I'm not gonna do this here. Instead, I will also create a random vector of size 3 by 1. Now what I want to do is I want to solve the linear system ax equal b, right? So I want to find the vector x so that a times x is equal to b, one of the most fundamental operations in numerical linear algebra. The command that Matlab is actually famous for is the backslash operator. So if you type x is assigned the value of a backslash b on the command line, then this will solve the linear system ax equal b. So the right-hand side is b, and assign the result to the vector x. So let's just do that. Here we are. So x is this vector here, and we can now verify that ax is equal b by computing the residual, right? The residual of a linear system is defined as the difference of the right-hand side b and a times the solution. So a times x, that would be the residual of this linear system. And you see that it's a vector whose entries are all in the order of unit round of 10 to the minus 16. So very small, and therefore we are happy. We have computed the answer to this problem to double precision. Okay, so backslash operator for solving linear systems, very important. What else do we have? We have other commands like the condition number of a matrix. So if you type cond A, that gives you the condition number. And if you want to learn more about these, that should be part of the numerical linear algebra course you might be taking this semester. It is basically a quantity that tells you how linearly independent the columns of the matrix are, right? So if you have two columns that are very, very close to each other, they point in the same direction, then you have a matrix that is ill-conditioned and it would have a large condition number, whereas the condition number is 1 for a matrix that has orthogonal columns. So for example, the condition number of the identity matrix would be 1. We can try this out, right? So if I take the identity matrix and I call it B and I type cont B, that would be a matrix that has a perfect condition number. Okay, 1 is a perfect condition number. Whereas if I have columns that are nearly linearly dependent, I get a very large condition number. Let's try this out actually. How can I make the columns of this matrix B almost linearly dependent? Well, what I could do is I could maybe try to make the second column almost the same as the first. So what I'll do is I will take the second column of my matrix and I will assign it the first column. Now I have two linearly dependent columns, right? The condition number of this matrix should be infinity. That's what we find. But now I could add a very, very small element to the position 2, 2, let's say, right? So that these vectors are not exactly linearly dependent. So for example, I could say that B22 is EPS. Okay, so a very, very small number. You see, it's not exactly 0, but it's very, very close to 0. So what's the condition number of this matrix? It's huge, it's like 10 to the 16. So when we solve a linear system with this matrix, we will expect that the entries are very, very sensitive to perturbations. Okay, that's what the condition number tells us. Let's have a look at some other commands. There is the rank. The rank of a matrix is the number of linearly independent rows and or columns. Sorry, I want the rank of A. The matrix A that we have here has apparently 3 linearly independent rows and columns. There is a command called null. This computes a basis for the null space of a matrix. So the null space is a set of column vectors, so that when you multiply A times these column vectors, you get the 0 matrix, right? So the null space is implemented in the null command, and we have a function for the norm of a matrix. So norm of A will give you the norm. I think by default it would be the 2 norm, but you can also compute other norms like the Frobenius norm, for example, by typing norm A, and then as a string you provide FRO. So this is the Frobenius norm of a matrix. If you want to learn more about these, I would assume that in the documentation you have some more explanations here. Of course, it also works for vectors, right? Because vectors are just special matrices. You can use the same function for that. And you see here, the 2 norm of a matrix is what you get by default by just typing norm and then the matrix name. And this corresponds to the largest singular value of a matrix. Whereas the Frobenius norm of a matrix calculates the 2 norm of a column vector. So if you transform your matrix into a column vector by just stacking all the columns on top of each other and then compute the 2 norm, then you get what is called the Frobenius norm of that matrix. Okay, so all of this is implemented. You don't need to do any of this yourself. You can just use the corresponding functions. Can have a quick look at exercise number 5. This is an interesting problem about a magic matrix. Okay, so there's a command in Matlab called magic that creates magic squares. So for example, if you type magic 5, you will get a magic square, which has the properties that all the row sums and column sums are the same, right? So if in whatever direction you sum this, you will get the same sum. And we could maybe solve a linear system with this matrix. So let's say my right-hand side is the vector of all ones. Might be interesting to find out what is which vector x satisfies the property that ax equal b, right? So x can can be obtained by using the backslash operator. So I'm solving a backslash b here, and we can look at the result. So this is the vector x that solves the linear system involving the magic square here. Do we notice anything particular about this vector x? If you see anything, please type it in the chat. Okay, yes, we see that all of the entries are identical, right? They look the same. And can we find out what these entries are? Yes, because as I just mentioned, A has constant row and column sums. So let's just look what is the sum of the entries along the rows. So I can do this by just typing sum A, 2. And we'll find that all the row sums are 65. So by the definition of a matrix vector product, what I need in order to solve a linear system so that the right-hand side is constant 1, my vector x needs to have entries 1 over 65 in each position. Right? So we can check this. What is x minus 1 over 65? That will take every entry of the vector x and subtract 1 over 65 from it. And we find indeed this is a very small number, again below machine epsilon, but it's not exactly 0. Right? So what we have computed, the x that we have computed, is of course only an approximate solution to the linear system we have solved. And therefore, we cannot expect all the entries to be exactly 1 over 65. In the handouts, exercise 5, there is a bound, a numerical bound for the solution of a linear system involving the condition number of a matrix. And I will leave it to you as an exercise to verify this bound. Okay, so for this, you need the approximate solution x, and it should satisfy the 2 inequalities that are listed there. All right, so let's have a quick look at some of the other commands. There is a QR command. Again, everything can be accessed with help. So if you type help QR, it will tell you that this computes an orthogonal triangular decomposition of a matrix. So if you just try this out with our matrix A, I can type square brackets Q comma R is QRA. So let's unpack this. This is the first function that we are calling, which returns more than one output. So this is the name of the function. It's QR. The input argument is A, our matrix, in this case, our magic square matrix. And on the left of this assignment operator, we now have square brackets, and we take 2 of these outputs, Q and R. So this is how functions work that have more than one output argument. You put them in square brackets and you give them names. So in this case, the output arguments will be 2 matrices, Q and R, and I will call them exactly in that way, Q and R. So when I hit enter here, then in my workspace, I will find that there is now a 5 by 5 matrix Q and a 5 by 5 matrix R. And by definition of the QR decomposition, they have the following properties. When I take A and I take off QR, this will give approximately 0. So Q times R is equal to A. That's the definition of the QR decomposition. And Q has orthonormal columns. It's an orthonormal matrix. And I can check this by computing Q transpose times Q. Okay, the definition of an orthogonal matrix is that this is equal to the identity. And indeed, we find that this is the case. Okay, you see this is 1s on the diagonal and approximate 0s on the off diagonals. And the matrix R is an upper triangular matrix. So all of its entries below the diagonal are equal to 0. And again, we find that this is the case. Right? So this is the definition of a QR decomposition of a matrix. It decomposes your matrix A into a product of an orthogonal matrix and an upper triangular matrix. There is something called the Scholeski Factorization, which is done with the Schol keyword. But this only works for symmetric positive definite matrices. So it would, for example, fail on my matrix A here. MATLAB is complaining that A must be positive definite. There's the Schur decomposition and the eigen decomposition. Maybe let's have a look at the eigen decomposition of our matrix A. So if I want to find the eigenvalues of A, I can just type eig A in MATLAB. All right, so these are the eigenvalues, 65, and then we have some others. Now the 65 we have seen before, right? This happened to be the number, but that was the row and column sum of that matrix. So it is not surprising that 65 is an eigenvalue, because we have just seen that when I take the vector of all ones and I compute A times the vector of all ones, I get 65 times the vector of all ones. So the vector of all ones is actually an eigenvector of this matrix. Just as an interesting side remark, it is actually known by theory that the eigenvalue of largest modulus, which is this one here, 65, is real and positive. There's a theory called Perron-Frobenius theory. You might have heard about this before, which guarantees that a positive matrix, which A certainly is, all the elements are positive, has an isolated eigenvalue, which is real, that is among all the eigenvalues, the one of largest magnitude. Okay, so that would be the eigenvalue 65 here. So maybe not so surprising that we see this eigenvalue 65. Also very important decomposition is the singular value decomposition, which is SVD. So if I want the singular value decomposition of my matrix, I can get 3 outputs actually, U, S, and V. Let's just do that. So we're not going into details about the definition of singular value decomposition here, but it turns out that this is a decomposition of a matrix into 3 factors, U times S times V star. So this should be similar to A. So let's just look at the difference. Again, that's fairly close to 0. 10 to the minus 13 is the magnitude of these entries. And these 3 matrices have the following properties. U and V are both orthogonal matrices. U is orthogonal, V is orthogonal, and S is a diagonal matrix with non-negative entries. Okay, these are the so-called singular values. So the way they are outputted here is as a diagonal matrix S. So if you just want the singular values of a matrix, you can just type diag of S, will extract you the diagonal, or you can just type SVD of A in the first place, and it would also just return you the singular values of A. Finally, you might be interested in computing FFTs. So if you work on a signal processing problem, for example, FFT of a vector computes the frequency components of that vector. Right, so I know this was very quick. There are 2 exercises which I left for you, exercise number 5 and 6. Exercise 6 is what I have already briefly discussed, the relation to the Perron-Frobenius theorem. If you want to learn more about any of these functions, again, just type doc and the function name or help and the function name, and you will see lots of examples relating to these. Right, so if there are no questions, I can't see any on the chat at least, I will just move on to section 5, which is the last one I want to cover before the break. Okay, this is about graphics. So it's a bit more exciting than just typing stuff into the command window. There is again a list of commands that we need. They are just listed there, starting with the figure command. So if you type figure, MATLAB will open a new window for you to plot on. So this is a figure window. I'm just bringing this in here. So this is how an empty figure looks like, right? And we can close a figure by just typing close. It's gone. Right? And the way plotting in MATLAB works is by generating vectors for the coordinates you want to plot. Let me just show you this at an example. So let's say we want to plot a function. Let's say we want to generate something that looks like a graph of a function, like so. Then in the simplest case, we just have like a 2D plot where we have an x-axis and the y-axis. And because in Matlab, everything is a vector, when we want to plot something, we need to first discretize it. Okay, so if I want to follow example number 7 on the handout, which is about plotting a sine function, a sine wave, over the interval 0 to pi, then the first thing I need to do in Matlab is I need to generate a vector that has entries in this interval 0 to 2 pi. And most conveniently, of course, I want to use equispaced points here, right? So I will generate a vector x whose entries are equispaced between the interval 0 to pi. And then I can define another vector y as sine of x. Now this again will be a vector. If I then give this vector together with x to the plot function in Matlab, what we'll do is it will take the elements in the x vector and the corresponding elements in the y vector, and it will plot them like so. So really what it's plotting is not like a continuous curve, but it's plotting the elements of two vectors depending on the coordinates indicated in x and y. Right? Now what Matlab does is it will actually by default connect these points by straight lines. And therefore you get the illusion that you're looking at a continuous function here. But really what we have done is we have discretized that function and plotted it. So let's follow this example in Matlab, example number 7. I will generate a figure, and you can, by the way, give numbers to figures. So my figure number 1 is this one here. Very often when you type something on the command line and you work with figures, the figures disappear in the background. So when I click here, the figure disappears in the background. It's still there, but not visible. If you want to bring it back up, you can type SHG, show graphics, and you'll see your figure again. Now, I want to plot the sine function over the interval 0 to pi. So I need to do exactly what I just explained. I need to discretize this interval into equidistant points. And luckily, we have already learned about the Linspace command. So I want a vector with equispaced points between 0 and 2 pi. And how many points should we choose? Let's maybe, for the beginning, use just 20 points, just to see what happens. So here's my vector of 20 equispaced points between 0 and 2 pi. I'm going to define another vector fx, which is sine of x. So this will now also be a vector that has 20 elements corresponding exactly to the sines of each entry of x. And what I can do now is I can say plot x fx. And in order to see the result, I need to bring up the figure, so I type hg. Okay, so this is the output, and you see it pretty much looks like a sine wave, but it's a little bit rough around the edges here. You see it's not really round. And that's because we have only used 20 points. So what I recommend if you do plotting 2D plots, I will use at least 200 points here. So if we just do the same here, I redefine my vector x to now have 200 points. I redefine fx to have also 200 points. Now if we do the plot, we will see that the result looks much more pleasant. Why are we using SHG? Because this figure here is kind of an independent window of Matlab's window. So for me, at least on my screen, because it's not big enough, when I work in the command window, it disappears in the background. So SHG just means show graphics. Right? So it brings back the figure to the top, so we can actually inspect it. Okay, so this is already nice. Now, according to the exercise, I also want to plot the zeros of this function on the interval 0 and 2 pi. So we want to plot something on top. If you want to plot two functions in the same figure, you need to hold the previous figure. And the way to do this is with the command hold on. Okay, so this will now hold this plot that we have generated. And we can now plot the zeros on top. So what I'll use is, what are the x coordinates of the zeros of the sine function? Well, they are at 0, pi, and 2 pi. You see, I've just created a vector with 3 elements corresponding to the roots. And what are the y coordinates of the roots? Well, by definition, these are just zeros, right? So here are 3 vectors with 3 elements for the x and y coordinates. And I want to plot them on top, and I want to plot them as red circles. So it's quite handy in Matlab. You can easily specify colors. So red is specified by the letter R, given as a string, as you can see here. So quote R. And if you want to plot circles as the markers, you just type O, right? So RO will correspond to red circles. Closing this string here, closing the bracket of the plot function. And if I hit enter now, and I bring back my figure, I'll see that I have plotted these roots on top. Nice. There are a few things I don't like here still. First of all, my x-axis extends up to 7, but really my function stops at 2 pi, right? What can we do about that? I can just change the limits of my x-axis using the command xlim. So xlim takes an input argument, which is a vector, where the first entry is the left endpoint of the x-axis, comma, and then the second element is the right endpoint of the x-axis. So if I call xlim with this vector having 2 entries, and I bring back my figure, we have changed the x-axis to just range from 0 to 6. There's also a ylim command, which can be used to limit the y range. X-label and y-label, pretty much as you would expect, they put labels on the x and y axis. So I could write, this is the x-axis, and it appears here as a text. Likewise, y-label. We have a function called legend. So legend takes a list of strings as inputs. So for example, I have just plotted the sine function. So I want to tell the viewer that the first function that I've plotted is the sine function, and the second was its roots. So if you use the legend command like that with a list of strings as inputs, then it will put a legend on your plot, like so, right? The blue curve corresponds to the function, and the red circles are its roots. Title is useful. So title, again, takes a string. You can put anything you like here. It will then appear in the title of your plot. Okay, so you can name them. And also grid is a useful command that I use quite often. So if you type grid on, it will put this nice grid in the background, so you can actually measure. You can somehow read off the values quite easily. For example, for x 2.5, the corresponding y value is approximately 0.6, right? That's what the grid is for. You can also turn off the grid if you don't like it by just typing grid off. And many of the commands in Matlab are like this. So for example, hold on also has an equivalent called hold off. If you want to stop drawing on top of this picture, you can use hold off for that. Right, so this is actually all these commands that I went through are also shown in examples 7 and 8. So hopefully you can just play with these on your own. Let's move on to exercise 9. This is now plotting a function in 2 dimensions. Okay, so how do we do this? Let me just clear this, and I will create a new figure, and I will use figure number 2 for that. Now, if we want to plot in 2 dimensions, again, we need to discretize the range we are plotting over. So we now want to plot in 3 dimensions. So we have a situation like this. We might have an x-axis and a y-axis here, right? And we now want to plot a surface. So let's say this is the z-axis here. We want to plot some kind of surface. something like that, right? So how to do this in MATLAB? Well, again, we need to discretize the XY range. So if the surface is plotted over a rectangular region in the XY plane, like so, so this would be the region we want to plot over, okay? Then what we now need is a discretization of points lying in this rectangle. Right, and a convenient command for creating such discretizations is called mesh grid. The way mesh grid works is it takes two input arguments, x and y, which are vectors. So x and y are both vectors, and in this case they would correspond to the x coordinates of our grid and the y coordinates of our grid. So it's a regular grid where the x coordinates and the y coordinates are follow the spacings indicated by the x and y vectors. Now, importantly, the output of mesh grid are two matrices, and I typically call them capital X, capital Y, because now they are matrices. These are vectors, and these are matrices. And these matrices are organized as follows. Along the columns of X, you will have a variation of the X entries according to what is written in the vectors in the vector X. But along the rows, the entries in X will be constant. And in the matrix Y, it's exactly the opposite. So along the columns of Y, you will have constant Y entries, but along the rows, you will vary along the values that are specified in Y. Let me just show you an example in MATLAB because it's much easier to understand, I believe. So let's generate a vector X that has X coordinates 1, 2, and 3. And just for sake of making it easier to read my vectors, the Y components, I want to range between 4, 5, and 6. Okay, these are my two vectors. And I now call mesh grid of X, Y, giving these two vectors as inputs and taking as outputs the matrices X and Y. So let's look at these matrices. The matrix X has entries that are taken from this vector X, right? So you see only 1s, 2s, and 3s, and you see it's constant 1 along the column 1, constant 2 along column 2, constant 1 along column 3. On the other hand, the matrix Y is constant along rows. So the first row is 4, which was the first entry in Y. Then we have a row of 5s and a row of 6. And the idea is that when you take any combination of these two matrices, so let's say you take the combination of point in position 3, 1, both in the X and the Y matrix, you get every possible combination in this XY grid. Right? So every point in this regular rectangular grid that we have generated can be obtained by looking at one position in the X matrix and the corresponding same position in the Y matrix and extracting the corresponding X and Y coordinates. Okay. So this is how MATLAB, how the 3D plotting functions in MATLAB work, usually using this mesh grid. So I will just copy and paste the example 9 from the handout. So here we want to plot a function over the interval -1, 7 in the X direction and -1, 1 in the Y direction. So I define these two vectors X and Y, and as before, I will generate a mesh grid. Now these are 200 by 200 matrices because I'm using 200 points in each coordinate direction. Now in this example, I want to plot the absolute modulus of the sine function of X plus Iy. So I want to plot the sine function over a complex domain. So in other words, the values in X are the real parts and the values in Y are the imaginary parts. For convenience, I will create a matrix Z as X plus 1i times Y. This is now a matrix of complex entries, which are exactly aligned in this two-dimensional grid. I can now define the function of interest. So I want to look at the sine function of z, and I will store the values I want to plot in the matrix F. And now I can call the function surf, the surface function. So this function takes as input x and y, which are our x and y coordinate grids, and then the function we want to plot. Now f has complex values, so I can really only plot the absolute part of this, or the absolute modulus of these complex numbers, because I have only 3 coordinates available. X and y are 2 coordinates, so I have only one more scalar coordinate. I will plot the absolute value of f. And let me just do this and show you how this looks like. So this is a plot of the sine function in the complex plane, where the imaginary part ranges between -1 and 1, and the real part varies between -1 and 7. Okay. Now, it doesn't look very good. We don't see much here. The reason is that Matlab by default plots like a black mesh over the surface. Okay, so you can't really see this, but there are like very fine black lines. We don't want them for this example. So we can remove them by giving another parameter to the surface function, which is documented, of course, if you type doc surf. What I want is, I want to change the line style of this mesh to none, which essentially means removing all the lines, right? When you change the line style to none, they will disappear. So if I go back now, I get a slightly nicer plot. And as you can see, I only wanted to plot from -1 to 7, but again, my axes extend a little bit too far. They extend to -2, 8. You can get rid of this by typing axis tight. So this will shrink the range of the x and the y axis exactly to the range that you have provided in the mesh grid command. So now we have nice axes here. And there's another command called color bar, which is often used in combination with surface plots, which tells you the values of your function dependent on the color. Okay, so I'll just maximize this. Here's my plot. If you hover over it, you will see this little menu popping up here, where you can, for example, rotate this graphics in 3 dimensions. Okay, so in fact, when I rotate it like this, you might actually see that this looks very much, if I go along the y=0 axis, which is this one here, the function that I'm looking at looks very much like the absolute modulus of the sine function, right? This is in fact sine of x, or absolute sine of x, that we see here. But then if we move this a little bit, we can actually see the extension of this function into the complex plane. So that's the sine function plotted over a region in the complex plane.